Okay, so vector basics. Today I'm going to be talking about, what vectors are. I'm going to talk the three key terms that I have in the corner there. The phrase tip to tail. I'm talking about that. Resultant vector, and then the term components, and just in general, how vectors work, how to think about vectors. Tomorrow I'm going to more explicitly go over how to add or subtract vectors graphically and mathematically. Okay, so by the end of class tomorrow, you should be, solid on vectors, which we're going to be using in doing two-dimensional motion problems, projectile motion. All right, so for starters, what do we mean by a vector? A vector is a measurement that has magnitude and direction. Okay, so what are examples of vectors? Well, we did some already in the first chapter. Displacement, not to be confused with distance. Distance is the scalar cousin to displacement. Displacement is a vector, which means it has direction. What else is vector? Velocity is a vector, not to be confused with the cousin speed, which is scalar. So velocity is vector. What else? Force, which we haven't talked about yet. Force is defined as any push or any pull. So obviously there's going to be a direction. Did I say acceleration yet? Acceleration is a vector. Momentum is a vector. Anything that has a direction included is a vector. Okay, now how do we draw vectors? Well, I got this diagram here of this guy driving his car. He's driving his car towards the left, so we could show his velocity with an arrow. So we say, oh, this guy is driving to the left with a velocity of 5 meters per second. We show vectors as arrows. And that's a real convenient thing to use because, the arrow shows the direction, and then how do you show the magnitude? By the size of the arrow. A short arrow indicates small magnitude. A long arrow indicates larger magnitude. All right, now looking at this diagram here, these 4 vectors. So you got 4 vectors on an XY axis. Are those 4 vectors the same or not the same? How many of you say those 4 vectors are the same? How many of you say they're not the same? Well, as far as I can tell, they're the same. Because why? They all point in the same direction, and they all have the same length, right? So look, one thing to know about vectors. You are allowed to pick a vector up and move it to another spot as long as you don't change the direction or the magnitude. You can move vectors around. In fact, you're going to be doing that quite a bit. You're like, all right, let's redraw this vector here. Okay, that's a big part of working with vectors. So these 4 vectors are the same. All right, now in your notes, I want you to write down these 3 terms and leave space to write something about each one. So I want you to write down the term or the phrase tip to tail. I want you to write down the term resultant vector, and then I want you to write down the word component. These are 3 very important words. Okay, the first phrase, tip to tail. Here's what I want you to write down for the phrase tip to tail. Vectors being added are always placed together tip to tail. It's a very common vector thing to know. Vectors to be added must be placed together tip to tail. Okay? Next term, resultant vector. The resultant vector is the answer that you're looking for when you're adding up 2 or more vectors. If you're taking 2 or more vectors and adding them together, the answer that you're looking for is referred to as the resultant vector. Okay? And then the next thing I want you to know about resultant vector, arguably more important, the resultant vector always goes from the tail of the first vector to the tip of the last. The resultant vector always goes from the tail of the first vector being added to the tip of the last vector being added. Okay? And then lastly, the term component. Now look, what does components mean? We use the word component in everyday life. A component, like, hey, so sitting here I have my computer and I got, this microphone that's recording my lecture, and I got my bamboo tablet here. I could refer to these as components, right? They're components that make up my computer system. Or if you buy something for your car stereo, you would call that like, oh, I got new components. Components are parts that make up the whole. That's it. So let me show you what that would be with vectors. And so I'm going to erase this. So say we kick a soccer ball, okay? So here's a soccer ball, and let's say the soccer ball gets kicked with a velocity of 5 meters per second at an angle of 30 degrees. Now, here's the x, here's the y. Is the 5 meters per second perfectly in the x? No. Is the 5 meters per second perfectly in the y? No. It has components. So I'm going to show you what I mean by components with a red pen. So I'm going to get red here. So this would be the x component of that 5. This would be the y component of the 5. Does that make sense? Okay, so the y component here, I'm going to show you later in this lecture later today, I'm going to show you how to figure this out, although I bet most of you could. Look, this would come out as 2.5 meters per second, and then the x component comes out as, let's see, sorry, I got to calculate this, 4.33. So, here's how you look at this. The x component and the y component added together gives the total vector, which is the 5 meters per second. So look, I want to point something out. Vectors to be added. How do you place vectors to be added? Tip to tail. Check this out right here. The x component and the y component. How are they placed together right there? Tip to tail, right? We're adding them. If you take the x component and the y component, put them together, it's going to give you the total vector, which is referred to as the resultant. Now notice that the 5 meters per second, the black vector there, notice that it goes from the tail of the first to the tip of the last, right? So everything I just told you is demonstrated right there. So we would call this guy the x component and this guy the y component. You add them together, you get the 5. Now hold on a second. Did I make a mistake? Everybody look. What the heck, man? 4.3 and 2.5, does that add up to 5? Wait, 4.3, 2.5, that adds up to 6.8. Uh-oh. Did we make a mistake? No. Because look, I want you to remember something. In the world of vector, 2 plus 2 does not always equal 4. It doesn't. That would be the scalar world. If you're in the scalar world, 2 plus 2 is always 4. In the vector world, what's 2 plus 2? Anywhere from 0 to 4. You guys see why? So look, let's go 2 plus 2. Ready? Let's just say that this vector here represents 2. This vector here represents 2. If you add those together, what would you be doing? You'd be going, okay, I'm going to add those two together. You place them how? Tip to tail. So you go, oh, 2 plus 2, that's 4. That's one extreme. But what if you had 2 and 2 where the other 2 pointed the other way? Then what would that give? 0. Then they cancel. All right. Hey, are you guys following this? Yeah. In the vector world, 2 plus 2 does not equal 4, because direction becomes a factor, right? Shh. What if you have a vector of 2 to the right and a vector of 2 to the left? What are those going to do? Cancel each other. And then you have all the possibilities in between, right? From an angle of 0 to an angle of 90. 2 plus 2 is anywhere from 0 to 4. So, hey, look. So my whole point in saying this is like, oh my gosh, we got 4.3 and 2.5. That doesn't add up to 5. Oh, yes, it does. If we apply what? Pythagorean theorem. What you want to do is you want to go this squared plus this squared equals this squared. Okay? We're dealing with vectors here, not scalars. Okay? So, tip to tail, resultant vector, components. Components are the parts that make up the whole. How are we going to be solving for components? With trig. I'm going to get to that a little bit later. Okay, now let's go to the next screen. Okay, so here, I want everybody just to copy this real quick. So copy down this situation. We're not going to solve this from, to its completion. This is just an example of like, how you would use vectors to figure out a physics question. Okay, so copy this down into your notes. Vector example. How many vectors do we have that are being added? So you got to read this paragraph. So helicopter starts in Inglewood, goes directly east for 15 miles, then it goes for 20 miles at an angle of 50 degrees northeast. So here we have north, south, west, east, like that. How many parts to the journey are there? 2. So Inglewood is like right about here. So what happens is the helicopter goes 15 miles. Oh, now notice in the bottom of the screen here, right here, notice we have a scaling. You're all familiar with scaling. Like this far is 5 miles. So you go, okay, so that far is about 5 miles. So I'm just going to eyeball this, right? If you were to do this like full on with graphical technique, you would want to have a ruler out and measure it so it's real nice. But just roughly speaking, so starting in Inglewood, 15 miles would be about that far right there. So there's 15 miles. We'll call this part A of the journey. We'll label this A. Now, the second part of the journey, 50 degrees northeast. So 50 degrees northeast is something like that, right? Where that's 50 degrees. So 50 degrees northeast, boom, for about 20 miles, a little bit longer. So that indicates, we'll call this part B of the journey, like that. The angle right here is 50 degrees. So notice, how do I have these two vectors placed together? Tip to tail. So if we wanted to figure out what the displacement of the helicopter was, and remember from last chapter, what does displacement care about? Starting point and ending point. The displacement would be that, from the tail of the first to the tip of the last. So I have this scanned in here. So here's vector A, right? 15 miles east. Here's vector B. Bam. Place them tip to tail like that, right? The resultant vector is going to be this, okay? Or in other words, like that. So we're just looking at how vectors work. Vectors, to be added, must be placed tip to tail. The resultant vector goes from tail of the first to the tip of the last, okay? Does this in general make sense? Okay, so a few more things and we're almost done here. We're almost done. Okay, I want to show you this. Okay, so what we're looking at here, this is 4 vectors being added. So I'll give you a minute, just copy this into your notes. Okay, so what's going on here is we're adding 4 vectors. Vector A, vector B, vector C, vector D. Notice all the vectors are placed together how? Tip to tail. Notice the resultant vector goes from the tail of the first to the tip of the last. This would give us, that's the answer you're looking for, if you added up those 4 vectors. Okay? Now, before we go to the next screen, if we added these vectors in a different order, so say for example we did vector D first, so there's vector D, and then we did vector A is like that, something like that. Let's just say you put them together in a different order. Would you get the same resultant vector if you did it in a different order? Yes, you would. It does not matter which order you put them in. You'll get the exact same answer, okay? All right, next screen. Okay, here, the key thing here is that we're looking at what happens if you're subtracting vectors. So what we're doing here is we're going vector A minus vector B. The whole point on this screen is that vector A minus vector B is identical to A plus negative vector B. Well, what the heck is negative vector B? What they're showing you in this diagram, this is vector B. See, they put it in there with dots, dot, 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 dot. So if that's vector B, what would negative vector B be? If this is vector B, then what's negative vector B? The same thing, but the other way. And that's what this is. Okay, so what did we put together in this vector exercise here? So here's vector A. Vector A is tip to tail with negative vector B, right? So really what we're doing is we're going vector A plus a negative vector B. You guys follow? So if you get a vector subtraction problem, just switch it around like that. So you got to go, okay, vector B, that's negative vector B. Just the same thing as vector B, but the other way. Everybody good? Okay, final thing, final screen. So we're going to talk about components again. So you need to be able to break vectors into their components. So let's look at the soccer ball being kicked again. So here's a soccer ball. It's kicked with an initial velocity of, let's say, 7 meters per second at an angle of 30 degrees. So what I want to do is I want to show the components and then solve for the components. So this indicates the x component of the velocity. This indicates the y component of the velocity. And again, like I said before, those are tip to tail. And the resultant vector runs from the tail of the first to the tip of the last. Right? So the black one, that's the resultant, that's the total vector, and then Vx and Vy are the components. Now, how can we get the components Vx and Vy? By using trig, right? So like for example, let's start with Vy. How could we solve for Vy? Well, we got this 30-degree angle, we have the hypotenuse, so what's going to do it? Sine, cosine, or tangent? Sine. So you go sine of 30. What's the definition of sine right here? Sine is opposite, which is Vy, over hypotenuse, which is 7. So Vy is going to be sine 30 times 7 meters per second, which gives us 3.5. All right, now how do we get the x component? Using cosine. So you're going to go cosine 30 equals Vx over 7. So Vx is going to be cosine 30 times 7, which gives us 6.06 meter per second. And like I just said before, realize that 6 plus 3.5 does not add up to 7 as it would if this were a scalar situation. But everything is correct, and you can verify it with Pythagorean theorem, right? This squared plus this squared should equal that squared, okay? So that's how you break vectors into components. It's just trig. Tomorrow what we're going to look at is we're going to go through in more detail, like how do you add vectors graphically, how do you add them mathematically.